Hello, in this video I'll be beginning to talk about another perspective on polar coordinates as they relate to complex numbers. So first of all, let's just remind ourselves, a complex number is one of the form a plus bi, where I is this imaginary unit, which is the square root of -1. So we introduce the square root of -1, and then we create a whole new realm of numbers once we use that in conjunction with real numbers. You certainly see this in Algebra 2, if not earlier, but I don't know to what extent it's really stressed that complex numbers are numbers. Pretty much whatever we do with real numbers or integers, we can do the same thing with complex numbers. Okay, and they can represent meaningful solutions. So just as an example, right, if I had gave you something like solve x squared plus 10x plus 26 equals 0, right, you've probably done an example like this. Here, just for simplicity, I'm going to change this to -10. If you tried solving this by the quadratic formula, we would have x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So we'll notice we're taking the square root of -4, which is 2i. And so our solutions are 5 plus or minus I. You could have gotten that by completing the square, and it presumably would have been faster. And I think this is often where people stop. Oh yeah, I follow these steps and then I just declare this to be my solution. But it really is a solution, right? Solutions are values that make the equation true. So this is checkable. What if x is equal to 5 minus I? That was one of our solutions. Well, let's see what happens when we take x squared minus 10 times x plus 26. So squaring means multiplying it by itself. I'll distribute that -10. This is getting a little busy because I didn't create a space for it, but I just want you to see this because I think this gets lost, that we really are genuinely solving the equation as opposed to getting some nonsense answer and putting it in a box. This part here I can FOIL. 25 minus 10i plus I squared. And let's see what happens here. This is 25. Sorry, this is 25. This is I squared, which is -1. So I'm just going to pay attention to the real numbers here. 25, -1, -50, 26. And so those cancel out to 0 real stuff. And then -10i and 10i, that's 0 imaginary stuff. So we really do get 0. It really is a value that makes this equation true. So what we do with numbers, we add them, we subtract them, we multiply them, we use them to solve equations. We can do that with imaginary and complex numbers. And by the end of this section, you'll see we can do even more exotic things that might not make any sense, at least right now. Now, I agree this is very abstract, and you may feel like, okay, I've gotten a solution in some algebraic sense, but how does this help us do anything? There really are cases where thinking about things in terms of the complex numbers allows us to do work more easily, and then at the end, all of the i's cancel out and we get a meaningful answer. So this really is a realm that makes certain things easier. Now, let's think about representation of complex numbers. every complex number has a real part and an imaginary part, so it's essentially two-dimensional. We can measure how much real stuff it has and how much imaginary stuff it has. And we can represent these numbers not on a number line, but basically a number plane. This is sometimes called an Argand diagram. And if we have the complex number a plus bi, we're going to plot it as though it's the point a comma b. So here is an example of the complex plane. What we would call the x-axis will now be called the real axis. And this would be our imaginary axis. Right? Some people use the word imaginary as synonymous with complex, and that's not accurate. Right? Imaginary numbers are the ones we get by taking square roots of negatives. Complex numbers are what we get when we throw in those imaginary numbers with real numbers and start combining them. So for example, right here would be 3 plus I. I've gone 3 units in the real direction and 1 unit in the imaginary direction. Right here, for example, would be negative 2 plus 2I. The real axis is the same as the real number line. Right? This point right here is 2. Right? It's 2 plus 0I, but that's just 2. So basically what we're doing is we're taking the real number line and we're imagining it as just one line passing through this entire plane. Okay, well, we've been learning about polar form. What if we try to represent a complex number in polar form? So I'm going to draw an example in the first quadrant. But everything else would work similarly. So this distance we'll call r, this angle we'll call theta. And so A is r cosine theta, and B is r sine theta. And usually we put the I in front, just out of habit, to make it clear that we're not taking sine of it. So this is the same thing. If we know what this distance is and what this angle is, the real part is basically x, that's r cosine theta. The imaginary part is basically y, that's r sine theta. So that's what we have down here. We will notice that the r can be factored out. That's very common. And for all kinds of complex numbers, it's always this pattern. Here is r on the outside. Here's cosine of an angle plus I times sine of the same angle. So sometimes people abbreviate cosine plus I sine as just CIS. You'll see another thing that's equivalent to that later on. In terms of vocabulary, in the context of a complex number, r is usually called the modulus. And it basically measures how big a complex number is. So sometimes we write it like absolute value. And this angle is called the argument. So let's just do a couple of examples. Here's Z1. Z1 is 4I. So that's here. It's 4 units away from the origin. The angle is pi over 2. So we could write this as Z1 equals R times cosine of theta plus I times sine of theta. Right? And you can check cosine of pi over 2 is 0, sine of pi over 2 is 1. So this is going to work out to be 4I. Here, what if we have root 3 minus I? Root 3 is approximately 1.7. So I've set this up that hopefully you notice it's 30, 60, 90. This would be 2. This angle here would be negative pi over 6. So we could say that Z2 is 2 CIS pi over 6. I'm writing it like that because I don't have a ton of space. I could expand it, I suppose. Well, this one is similar to the other one. I'll skip it. Maybe I meant to say 5 or negative 5. You'll have some of these to practice for homework. Negative 6 minus 6i would be like so. So we have 45, 45, 90. This angle here is 5 pi over 4, or at least that's one option. And r would be 6 root 2. So this is 6 root 2 times cosine of 5 pi over 4 plus I sine of 5 pi over 4. If you know how to convert to polar coordinates, we're just using this in the context of complex numbers.